So, this is a presentation for SmartPatch, improving handwritten word imitation with patch discriminators. So first, the outline of the talk. We're going to talk about offline and general handwritten text generation first. And we talk about the prior art, Handwriting. Then we introduce our methods and we also show the benchmarking. So first, what is handwritten text generation? Well, and why should I care even? So the use cases for handwritten text generation are basically twofold. One is in machine learning and pattern recognition, and there we have data augmentation. Obviously, if you don't have enough data, you can just generate more. It's also the second one, balancing classes. So if there's one class we have vastly more labels, vastly more samples than the other, then you can like balance out the different classes by just generating more. This is especially relevant for like historical data sets where imbalance is kind of to be expected. We can also make handwritten text editable. For example, here in this example from the paper Deep Writing, you can see that they are able to take this text, so just can't get enough, and can change the get to write. It's also useful for accessibility. So, for example, Parkinson's patients are now able to like write in their own text again, and it's also useful for realism in media. So, for example, in like virtual reality, you're able to take your own handwriting with you. So, but how should you do that? For this, we discussed the prior art, Handwriting. So, what Handwriting does is it's a generative adversarial neural network, and it consists of two parts. One is the generator, which gets style and content. So, style are just 50 samples from the same writer, and content is just one hot encoded text. And they generate a word which has the style of the examples and the content of the content. And then we have a normal GAN discriminator, which tries to distinguish between fake samples and real samples. We also have an HDR model, which tries to detect the content, and a writer identification, which tries to detect the style. And the idea is that both of these losses together allow the generator to disentangle style and content, so you get independence from both of these things. So GAN writing already works pretty well. However, it also has some problems. So these are some frequent defects. If we look here on the top left, we have this stepping artifact, which happens a lot. Then we have these thin lines, for example, here the E in the middle of the word, which suddenly becomes very thin. We also have these smudged lines, which here in the H, for example, it's here the tail here is very smudged. And we have the unsteadiness here in the R. Now, all of these also happen in the real data set. However, GAN writing produces them a lot more often and with a lot higher intensity. So you can expect, for example, some dried out pens in the dataset, but not to that degree and not in the middle of the word with the rest of the word now still being normal. So our methods obviously now try to solve this. And the idea we had is we use a naive patch discriminator, so which is a dedicated discriminator for the character level, which just takes rolling patches of 64 by 64 size with a stride of 32, so you always have 50% overlap, and a small discriminator, which is a pix-to-pix style model with a receptor field of 70 times 70, so it's the smallest one that covers the entire patch. And we now train this also with the rest of the model. So this is how that would look like. However, you can already see some problems. So first of all, you need a lot of patches to cover the entire text piece entirely. And there are also some phantom characters. So if you look, for example, here, we have the N here, which is a phantom character which happened through the splitting of the M here. So how could you solve this? We could simply solve this by just having one patch for each character. And this is our second approach, which is centered patch. And the idea here is we localize the different characters through the recognition model. To do that, we linearly upsample the attention, and standard patch on the maximum. We maintain the same network as a naive patch. And as you can see, this localization already works pretty well. This is how the model now looks like. We take the HDR attention mask and center the patches on that. And as you can see, we now don't have the phantom N, and we have fewer patches. And of course, we can extend that a little bit further still. And the idea is because if we now split based on the characters, we can also just inject the character information into the discriminator too. So the idea is we use the ground truth labels instead of the predicted ones from the recognition model. We linearly project them into an 8-dimensional space and just add this dimension to the pix-to-pix, so in the middle of the network. The size now is approximately the same as naive and standard patch. It's a little bit more due to the projection and the appending of the text, but that's insignificant in the whole scheme of things. Now let's look at benchmarking. First, some qualitative examples. So as you can see, here on the left of GAN writing, we still have this stepping and this shallow E, and this is now missing from the SmartPatch method. So at least from this example, we can see it had worked. So for the further benchmarking, so for the quantitative one, we use a synthetic EM approach. The idea is we just recreate the EM dataset. So for each they of a certain writer, we produce a they of the same writer. And we shuffle style images if we want different instances of a word. So for example, if one writer has written with 20 different times, we just shuffle the style inputs and get 20 different widths. In general, we get at least 50 factorial different options, so that should be enough noise for our purposes. The first thing you usually test in generative models is the FID, so Frisch inception distance. So ours performs better than the prior art. However, we also argue that FID is a bad metric for handwritten text generation. We're not the first ones to do so, and the arguments are basically the following. Inception is a network trained on ImageNet, so on naturalistic object images, and not, for example, like shallow and monochromatic text. So the embeddings might not be perfect. It's pretty hard to interpret the results. So what does an FID of 40 mean for like objective image quality? And it's also hard to test the conditional generation, which is also why we basically standardize it on our synthetic EM approach. So one way we try to solve this is by introducing a new benchmark, which we call the HDR benchmark. The idea is we evaluate an HDR system that is trained on the real data on our synthetic dataset. To do that, we use Kang et al.'s HDR system, which we chose because it's a state-of-the-art system, and also it's different from the one that's used in GAN writing. So if GAN writing introduces some kind of bias using the model selection, we now don't have that in our HDR. We have multiple evaluations for the standard deviation, so we generate multiple synthetic EMs, and we have now the advantage of having interpretable results. So a CER of 4 means exactly 4% of the characters are either missing or wrong or swapped around. As you can also see, we have the lowest standard deviation, meaning that at least from that point of view, from this qualitative point of view, it also seems that our method tries to preserve the content a little bit more. And the disadvantage of this technique, to go back, is that it only cares about the content. It doesn't care about the style. Similar to how FID only cares about the style and not about the content. To put both together, we also have a head-to-head comparison of different techniques in a user study. Additionally to the technique GAN writing and real data, we also compare with line gen, which is a technique by Davis et al., which is a contemporary technique and was trained on entire lines. So why this is important, you're going to see when we discuss the results. But first, let's look at how we prepared the samples. We always picked a sample from 2 datasets. It's always the same sample, so if if we pick writer number 25, then we also pick writer number 25 from a different data set. It's always the same content. We then scale it based on the existence of ascenders and descenders. Then we have white noise in the background. And we randomly place the images left or right. So sometimes SmartPatch is on the left, sometimes on the right. It's random. And our task was simply, well, pick the one that's more realistic. So these are results. And as you can see, SmartPatch outperforms everything else, especially also the real data. And that's quite puzzling because, well, it shouldn't do that. So why is this the case? Well, it becomes apparent if we don't split it head to head. So between the different tasks, between the different generation methods, but instead we split it based on length. So these are the absolute numbers of picks based on small, medium, or large words. And as you can see, ours outperforms everything, including real data, on small words. For medium length words, we are on par with real data. And for large words, real data outperforms everything still. But also, line gen starts to improve, which also makes sense because line gen was trained on entire lines, so it's used to having more characters. However, SmartPatch still beats line gen, however only by a small margin. So if we used maybe a little bit larger words still, then maybe line gen would outperform ours. So to answer the final question, why is our pick rate higher than the real data? Well, it all comes down to, well, this small category. And this small category, we can see that small hastily written words, for example, this to, may be interpreted as fake when compared to like the more clean SmartPatch examples. So for example, in this case, real EM does not have this horizontal line of the T, while ours has it. Now, if you give people the task of judging which one is real, standalone without further context, he's just going to look at it and see, well, here the horizontal line is missing, here it is there, so this one is going to be the real one. Further, things like dried out pens and stroke inconsistencies, which happen in the real data too, may just randomly elevate one dataset over the other, and this is just more apparent in small words. In conclusion, we show that language patch discriminators significantly improve the state of the art in handwritten text generation. We also show that methods that incorporate more prior knowledge outperform the ones that don't. And we also show that our method is superior by first FID, then our new HDR benchmark, and then a user study. Thank you for your attention.